Okay, so in the last video we looked at Taylor polynomials, and what we showed was that if you kept adding terms to the polynomial, the Taylor polynomial, it actually began to resemble more and more the graph of the actual function. So putting these ideas together, that we know a series is an infinite sum, and a Taylor polynomial is the sum to some n degree. A Taylor series is a infinite Taylor polynomial, and in fact, if you can create a series that converges for some select a value wherever we want to be centered at, it'll actually be the same thing as that function. And so we know how to find the individual term of a Taylor series, that it's the derivative number starting at n equals 0. We actually start with the regular function value. And we can create each term using this f to the n over a over n factorial x minus a to the n. So we can make these terms, and really, if you did an infinite number of the terms, you would end up with a series. Okay, so let's find the first four non-zero terms for the Taylor series of ln x centered at x equals 1. Well, if you recall, in the previous video, we actually already have done this Taylor polynomial. But for the series, the first four non-zero terms would be the same thing as the first four of the polynomial, which would be x minus 1, and then we got minus 1/2, x minus 1 squared, plus 1/3, x minus 1 cubed, and then the fourth term, minus 1/4 x minus 1 to the fourth. So we want to think, how can we write this as some sort of... And so the first thing I note, if you look at, we're going from positive to negative, and that would continue. So when I'm writing my sum, I'm going to start with negative 1 to the n minus 1, because that would make it rotate. And then the next thing I notice, the first term is x minus 1, and the next term is x minus 1 squared, x minus 1 cubed, and so on. So I know I'm going to have some sort of x minus 1 to the n. And then on the bottom, I'm dividing the first term technically by 1, the second term by 2, 3, 4. I'm dividing by n. Okay, and then when you think, well, what should n start at? We want the first term to be positive, so I'm going to start n equals 1 to infinity, because 1 minus 1, if I plug that in, would be 0, and anything to the 0 power is 1. So what we've done is we've developed a summation notation that represents that series. And so, in fact, this series is actually the exact same thing as natural log x. Okay, so now we're going to look at a way to actually quickly come up with some Taylor series of terms that look like they'd be difficult to do, but if we can find something similar that's simple, we can quickly come up with another Taylor series. So if we did e to the y, if you were to compute e to the y, the Taylor series, it would be this thing. 1 plus y squared plus y cubed, and so on, over 2 factorial, 3 factorial. But we want to do e to the negative x squared. So if I let e to the negative x squared be the same thing as e to the y, then y is simply the same thing as negative x squared. So to do e to the negative x squared, everywhere that there's a y, I'm going to replace that with negative x squared. So this Taylor series is going to be 1 plus, I'm going to replace that y with negative x squared, plus negative x squared over 2 factorial. plus negative x squared cubed over 3 factorial. So e to the negative x squared is the same thing as 1 minus x squared. A negative x squared squared would actually be a positive x to the 4th over 2 factorial is 2. The next one, a negative times a negative times a negative gives me negative x to the 6th over 3 factorial, which is 6, and on and on and on. We could continue that pattern. So if you know some simple one, like this, e to the y, and you had e to the negative x squared, you could replace all those y's with the negative x squared. So that's one way to quickly come up with the Taylor series. We can also use derivatives, and we can also use integration. So let's say that the given Taylor series below, I said f of x equals 1 over 1 plus x squared equals 1 minus x squared plus x to the 4th minus x to the 6th, and on and on and on. And I say, okay, use that fact to find the Taylor series for arctan of x. Well, the interesting thing about 1 over 1 plus x squared, that's the derivative of arctan of x. Or in other words, arctan of x would actually equal the integration of 1 plus x squared dx. Because the derivative of arctan of x is 1 over 1 plus x squared dx, you could do it the opposite way and do the integration. So because of this, then if we integrate 1 over 1 plus x squared dx, that would give us arctan of x. So really, we just need to integrate this series, each individual term. And on and on and on. So if we do that, if we integrate x, if we integrate 1, that's just x, minus, if we integrate x cubed, 1 over 3 x, if we integrate x squared, that would be 1 over 3x cubed. If we integrate x to the 4th, 1 over 5 x to the 5th, and so on and so on. The next one would be minus 1 over 7 x to the 7th. And this is, in fact, the same thing as arctan of x. So the fact that I could integrate this thing to get arctan of x tells me I can just integrate each term. The likewise would be true. If you knew something was the derivative of something else, then you could use the derivative to go the other direction as well.